Hello, everyone, and welcome to today's Elektor webinar. I see we have a lot of people in the chat room. Thank you, everyone, for joining us. I'm your host for this session, Brian, and we're diving into a fascinating topic, implementing edge AI solutions with Arduino Pro. Whether you're a developer, engineer, or just curious about the intersection of AI and embedded systems, you're in the right place. And we're honored to have Giampaolo Mancini with us today. Giampaolo is a senior customer success engineer at Arduino Pro, and he brings years of experience in IoT, embedded systems, and wireless technologies. So, Giampaolo, welcome to the webinar, and thanks for joining us.
Thank you. Hello, everyone. Nice to meet you, Brian, and everyone in the listening and in the chat.
Great, thank you. Let me just tell you a bit about Giampaolo. He's designed and developed state-of-the-art systems in ICT, focusing on embedded systems and IoT applications. And over the years, he's gained deep knowledge in wireless technologies, networking, machine-to-machine communication, and beyond his technical expertise, he's passionate about leveraging cutting-edge tools to solve real-world problems and drive innovation. So today, he'll walk us through some exciting possibilities with Arduino boards and edge AI, including a live demo, which is what you're all here for. So, Giampaolo, great to have you here.
Thank you.
Before I move on with Giampaolo, let me bring up our giveaway screen just to tell you what we're doing. Yes, we're giving away Arduino Nano 33 BLE Sense Rev2 with headers. An Arduino product, of course, and it's a versatile microcontroller. It's perfect for advanced IoT and edge AI applications. It's got Bluetooth low energy connectivity and multiple sensors for motion tracking, environmental monitoring, and sound detection. So stay with us until the end for your chance to win. There'll be a code word to punch in over here on this page, and I will give it to you later, as I always do, just to tease you right now. So stick around with us. And then, before we move on, once again, a bit of housekeeping. I want to tell you again about EE News Europe. If you're looking for the latest electronics and engineering news, check out eenewseurope.com, which is an Elektor international media publication. It's a fully digital publication covering the global electronics market with specializations in analog, automotive, embedded, power, smart 2.0, and wireless technologies. So read eenewseurope.com and subscribe to its newsletters to stay informed about essential industry news, key events, and technological innovations. eenewseurope.com, and that's the housekeeping, so I'll take that down and we'll get to Giampaolo. Thanks once again for joining us, and please tell us about your implementing edge AI solutions with the Portenta X3.
Yeah, it's a nice project, something to add to the awesome list of projects you had in your special issue on edge AI. I browsed it and I found a very interesting project, something different from the standard stuff, the usual stuff you find online. So I wanted to add something different also from our part. So the idea here is to use the Portenta X8, which is the Arduino board based on Linux and Docker containers, to implement a sensor future application using a new feature from Gimpulse, which is deploying machine learning models using Docker images. So I will show you how to integrate everything. So running the inference model on X8 in a Docker container and having a Python application getting data from a sensor connected to the Portenta X8. Actually, in the demo, I'm faking it using a special sketch and asking the model to run the inference and get the results. I will move on my slides just to give you in a row. The Portenta X8, it's, as I told before, our Linux-based machine. It is in the same form factor of the Portenta H7 and the Portenta C33. They have high-density connector on the bottom that allows them to be connected on carrier board, such as the one that I have on my desktop right now. So this is the Portenta X8 mounted on top of a Portenta hat carrier. So the idea of the webinar is to let you know how to configure the Portenta X8 with the out-of-the-box experience, how to collect data from the sensors using an Arduino Sketch, how to create and train the model using a Gimpulse, and the most important thing is how to deploy a Compose app, which is a special combination of Docker containers on the Portenta X8 to run both the inference and capture data from the sensors. So the interesting part here is that the Portenta X8 has actually two processors on board. The first one is an application processor running Linux. It's a four-core processor, and then there is also a microcontroller, an STM32H7, which is the same microcontroller we have in the Portenta H7, which is running a special sketch on its first core for duty task for extending peripheral features of the Linux core, and the other cores is available for running Arduino Sketch. So you can combine Python application and Linux application and Arduino application in order to achieve an hybrid system with quasi-real-time or real-time performances. To configure the Portenta X8, you can find a lot of documentation on the docs.arduino.cc website. And actually, it is pretty easy. You just need to connect the Portenta X8 to your PC and go to arduino.cc/start. And there is a wizard that will let you connect on the Portenta X8 and configure it. And then at the end, you will land on a special web portal, which is hosted inside containers on the Portenta X8 that allows to configure it. So also to connect to the Arduino cloud, to configure the Ethernet or Wi-Fi or whatever. So pretty streamlined, pretty simple. For collecting the data, you can use whatever. You can use also a different Arduino board connected to a sensor. You just need to implement a simple sketch, getting data from the various sensors connected to the board, and then format it one sample per line as a comma separated files, and then you can use the Gimpulse data forwarder tool to capture the data and send it to your project. This can be done when you start your Gimpulse project, or later when you want to check if the model is performing well, doing live test. Regarding the model I used in this demo, I actually started from an how-to that it's available on the Gimpulse website, which is a sensor fusion tutorial, which was originally done to be run on an Arduino 33 BLE Sense. But of course, it can be easily ported to any kind of Arduino boards supporting machine learning or AI, or any kind of system, because at the end, the important thing is the way you deploy the model. So for this project, the idea is to capture different kind of measurements from an environmental sensor. So I'm capturing temperatures, humidity, pressure, and gas, and I will let the model on a Gimpulse to fuse together this data to recognize the room I'm in. So I created three kinds of synthetic data set, emulating three different data with different temperature, humidity, pressure, and gas features. And I then will have my sketch in them4 simulating moving from one room to another and generating random data using a normal distribution centered on the features that I use to create the static data for the edge impulse model. And that's all regarding the creation and the training of the model. For everything I will show today, I posted all the code and part of the documentation on GitHub, on a repository we use to share projects with customers and partners and users. And I'm sharing also the edge impulse project I use to generate and to train the model. Okay, so first of all, I will show you the project on edge impulse. As I told you, I started from their tutorial. So I just ran the data acquisition. I created different data set collecting a few samples of 10 seconds of data for the different rooms. And for every room I generated data using different starting point from temperatures, humidity, pressure, and gas, in order to have a clear distinction of the different rooms. So I followed the usual step to create the impulse, to do all the optimization needed for the model to be run, and created the container. And at the end, of course, I ended with an accuracy pretty high because the data were generated synthetically. And I also ran a few live classification using the sketch I provided in the GitHub repository, and also the testing. Okay. So this is pretty standard. You can find information on how to do this on the linked tutorial on the slides that we will share at the end of the webinar. And the most important thing is that at the moment of selecting the way I would like to for deploying the container, I choose the Docker container. So when you have different deployment option, and you just search for Docker, and I choose the generic Docker container. Okay, and then you let Giampaolo run in order to create your deployment. And at the end, you will end with two important things. The first one is the code, the link for the image, the Docker image containing the model I want to run, and the other one it's an API key which is needed for the model to be connected to my project. You can run this model using Docker offline, of course, on your PC or any architecture that supports Docker. So an Arduino Portenta X8, a Raspberry Pi, a Windows computer, whatever. Everything that supports Docker can run this model using this kind of deployment. Okay. I share this project as a public project, so you can clone it and start using it right now. Okay, and then the second part, the most important, the other important part is to write an application to be run on the Portenta X8 that gets data from the sensors connected to M4 core on the Portenta X8. And then submitting the data captured from the sensor to the edge impulse model in order to run the inference and get the results. Okay, so I shared also the code for this application. I wrote it in Python, which is straightforward straightforward and easy to use. And I will show it in a few. I will just come back to the slides to let you know how the architecture of this stuff works. Okay, so as I told you before, on the Portenta X8, we have two different compartments. The first one is a Linux operating system based on Yocto and container running containerized application in Python or whatever language you prefer. And the other part is the Arduino Nano that can be programmed using both the classical C++ based language of Arduino or also MicroPython. In the Linux part, we have, for this demo, the Python container and the Edge Impulse container. And they run together as a single application using a system which is called, in the Docker jargon, a compose app, which is an extended application composed by two or more different services, all talking together using an internal shared LAN. So you can have different application, you can have web servers, you can have database servers or whatever, and they can talk each other using the same virtual LAN. So everything that you can use on Linux and on the web also works inside the Docker containers in Compose app. Okay, so the idea is here is to run the machine learning application on Linux and have the real-time part on the Arduino Sketch, because the Arduino Sketch is fast and can do stuff that typically it's quite difficult to do for microprocessor, for example, driving a motor or a strip LED, which are devices that require pretty tight timings that are difficult to achieve with generic Linux board, if not running real-time operating system, RTOS version of Linux. Regarding the ML application, on the Portenta X8, we don't have currently accelerator for machine learning application, but if, for example, you have an external machine learning accelerator, or you have another kind of a board that has ML acceleration integrated, you can leverage this stuff for the Edge Impulse container to use this kind of advanced MPUs for running the inference. So this application can be very, very fast, very, very responsive. So the way the Linux part and the Arduino parts talk each other, it's using an RPC mechanism, a remote procedure call. So what happens is that in Python or whatever language you choose, you can use a library to send a call to the Arduino part to get data or to send data, and this can be this conversation can be initiated by the Linux part. So it's the Linux application that it's requesting something to the Arduino Sketch, or vice versa. So it can also be that the Arduino Sketch requests something to the Linux part. So depending on the architecture you may want to implement, the initiator of the conversation can be both the Linux application or the Arduino Sketch, or together they can do the same thing together, both. So the rationale for this is that you can decouple the real-time part, the difficult part, in C++ or MicroPython to be run on the Arduino side, and have more complex application, for example, also for displaying data over an HMI panel, or exposing a web server with a graphical user interface for showing the data, having dashboards, or interacting with more complex system, something that can be difficult to do in Arduino itself. And for the other side, you can have stuff running in real time in the Arduino Sketch. So the idea is to run the machine learning part on Linux and the real-time part on the Arduino. And the demo I composed here, it's made by the three big elements. So we have a Python container collecting the data sensor via the RPC from the Arduino Sketch running on the Arduino 4, then sending all the data we collected. We need to collect 400 values from the Arduino Sketch and submit it to the Gimpulse container, then getting the results and then publishing the results to the Arduino M4 that can do something with this. In this example, I'm just blinking an LED, but for example, you can drive a motor, you can actuate something, for example, opening, closing a relay or whatever you will need. And the edge inputs container, it's something that I didn't brought. This is just the image that the edge impulse publish, so I don't have access to the code. It's just a black box which I use to submit data and get the classification. Okay, the communication from the Python container to the edge impulse container, it's done using HTTP and using a well-documented REST API. You can find all the information on the relevant, on the corresponding part on the documentation website from edge impulse. Okay, this stuff, those are user information for connecting the Portenta X8 to transfer files and to build and run the application. I will show you in a few. And let's back to the code. So pretty simple, actually, Python script using a few libraries. The main part, we just have a main that is at the end, it's doing a little bit of preparation, and then at the end of the main, I'm calling the method, the function that will get data from the sensor and submit to the edge impulse container. And it is pretty simple. It just collects data from the Arduino core. I will show the function that does it in a few. Then after running 100 times, we are collecting four values, so temperature, humidity, pressure, and gas, for 100 times in order to have 400 feature that we need to be submitted to the machine learning impulse. And then we just submit the data to the edge impulse container. The edge impulse container will answer with a JSON response. In the JSON response, we will have a couple of objects containing the results and the classification the edge impulse model has done, and then I will submit back the results of the classification to the Arduino M4 core using this call. So the call for getting data using the RPC for the M4 is pretty straightforward. It's just a couple of lines. So we are instantiating an RPC client using a predefined address for an agent which is running on the X8 that acts as a bridge between application and M4 core. And I'm asking it to call to request values for temperature, humidity, pressure, and gas. So here we have a Python list compression to get all the 4 data in one call. Okay, so at the end, I will have the 4 data in this value, I return it, and then I'm collecting 100 of those lists. And this is pretty simple, okay? Regarding the sketch, which is running in the M4, also it's simple. As I told you before, I'm faking having a sort of BME 6380 sensor connected. The important part on this kind of sketch, so sketch running RPC call, is that I'm not running the code for getting data from the sensor inside the function that manage the response from RPC, because it will be too slow. So in order to have the sketch to respond fast to the
Giampaolo, are you there?
Yes.
Oh, seem to have had a bit of an interruption there. I don't know if it was a network issue, but glad we're back.
So okay, so in the sketch, I'm declaring, I'm binding this lambda function to the temperature call. It's just a way to use the RPC library, and then I'm returning just the value I collected before. So in this way, I can have the RPC respond very fast to the call from the Python script. And in the loop, I will just have a function, a procedure running every 10 microseconds, 100 microseconds, that gets the data from the sensor. So this way, I can decouple responding to the RPC call and getting data from the sensor in order to have a very fast sketch and a very fast response to the RPC calls. Okay, so pretty simple. As I told you before, I'm simulating the sensor moving between 3 different rooms, and all the rest of the sketch, it's just managing, simulating changing the room every 5 or 6 seconds. So all the other functions are just helpers to make this happens. So pretty simple, pretty straightforward. Okay, so let's go to the demo, to the actual demo. So the code which is running on the Portenta X8. I will just change the share, the screen I'm sharing. Let me see. I can go from there. No, okay. I will share the entire screen then. Okay, and I will move to Visual Studio Code. Okay, and okay, so now I will connect to my Portenta using SSH. The slides, the deck slides contains instruction on how to do it. You can also find information on the Docs website from Docs Arduino website. So connecting. Okay, so I'm in. I have my application inside this folder. Okay, and I previously built the Docker container for the Python application, and I put together the Python application and the edge inputs container using the Docker Compose file. I will show it in a few. So the Docker Compose file is this kind of file. It's a file where you programmatically define how the different container will run using which parameters and whatever. So I'm defining 2 services. So the first one, it's the service which I called collect and dispatch, and it is the one which is running the Python application I wrote. And the other service, it's the inference service, which is just using the just using the image that Edge Impulse generated, and I'm calling it with parameters that you can find on the deployment page on your project, on Edge Impulse project. So pretty simple. And the way that they talk together, it's using an internal network, and the Python application will reach the Edge Impulse container using the name of the services as the name of the host. So this is the name of the host of this container running inside the Docker environment. So this way we can make the two services talk together. So when I run the Python application inside the container, it will reach the Edge Impulse container using this hostname inference, and will connect to the 13377 port. Okay, and back to the shell. To run all the application together, I just launch Docker compose app melody command, which dispatch the container in the background, and then I can see what is happening using the Docker compose logs command, which show what is happening inside the containers. So I let run it for a few, and then I stop to show what is happening. Okay. So the yellow line are the outputs from the Edge Impulse container, while the blue lines are the outputs for my Python application. Okay, so in the Python application, I'm collecting the 400 features I need for the model. Then I submit it to the inference container, and then the container responds me with its classification. So in the sketch, I'm simulating being in the room C, and I submit the features, and the model recognizes the room C, and I will submit the results back to the sketch. So if we let the application run, you can see that every 5 or 6 seconds the room will change, because the sketch will generate different values, simulating being in different rooms. And okay, so now it's moved to room A. And the model, it's recognizing that the sensor is the room A, and this is all. A lot of stuff, but mostly straightforward. Let me go back to the slides. So. Let me see if there is something more that I need to add. Yes, some more information. The RPC method we are implementing is based on message pack, and is called message pack RPC. There are libraries for a lot of languages. I use Python, but there are also for Go, for Java, for Node.js, or whatever. So you can implement your container for integrating everything in the language you prefer. And that's all for the moment. So, Brian, I think that we can ask people if they have question or need any information or clarifications.
Yes, we have a few questions. We'll get to them shortly. Let me put up the Arduino, the Portenta X8 page. You can see the URL here. I'll drop it into the chat. It is quite a capable board, and there's a lot of information there. So I've dropped the link in the chat, and yeah, you can see the documentation site there for the Portenta X8. Now, if I can start with a question, I see that you're using containerized applications, and I've only recently started using Docker. For example, I managed to run a large language model on a Raspberry Pi. What's the benefit of using Docker in a situation like this, containerizing the whole thing?
I started using Docker something like 10 years ago on a single board computer. And the reason was I wanted to be able to update and upgrade my application and the libraries they rely on without having to upgrade the entire system. Okay, so if you do a typical deployment of a Linux application on a standard Linux system, one based, for example, on Ubuntu or Fedora or whatever, every time you need to upgrade your application, you also need to upgrade libraries and all the stuff needed for your application to be run. And this is cumbersome. It can be pretty difficult to do. In some cases, it cannot be done because maybe you need a different version for a library which is not available to the packaging system of your distribution. And this is one of the most important features and advantages that Docker containers gives to you. So it's the ability to decouple the system your application runs in from the operating system, an external operating system. This way you can have, for example, different Python application using a different version of the interpreters, different version of libraries, and so you don't have to manage version clashing, different kind of requirements or whatever. And this was the main advantage for me. The other advantage is that as far as I can run everything in a Docker container, I can run it on a Portenta X8, on a Raspberry Pi, on a Linux machine, on a Windows machine, or whatever, without changing a single line of code. Because as far as I can build a new image for a supported operating system and architecture, the application can run unchanged on every kind of every kind of platform. So it's quite easy to test and develop it. So if, for example, you don't have your target port available, you can also start testing everything on your Mac, on your PC, and then move what you need on your final target only when it is available.
Well, I think that answers the question quite in depth, and you probably already answered Asma's question. Thank you for the question, Asma. It's in terms of how it empowers developers, especially when working with Edge AI. Yes, carry on.
Yeah. So I can get back to one of the slides. Yes, that one. So the idea is to allow users on the Portenta X8 to have a very stable and very secure base operating system running on Yocto, and a specialized version of Yocto which is called Linux Microplatform, made by Foundries, which is very focused on security and on stability. And then you can do all your kind of experiment or strange stuff using containerized application. Okay, so the idea is that you can have different environment, very different environment, all running in parallel, and everyone decoupled from the other. and not interfering each with other in terms of file system, libraries, and also security, because another important feature on Docker container is that you can choose what are the resources from the system you can share, both in terms of performance and also in terms of what can be accessed or not. For example, by default, Docker container cannot access the network or cannot access devices or whatever. You need explicitly tell what the Docker container can access when it is running. So this is a way to segregate application in terms of security and performances. Okay. Regarding Edge AI, this allows you, for example, to run a model using stable version, for example, for Python libraries that might require pretty old version of other libraries that can be maybe in common with the libraries that you need in your application, but in your application, you need a most recent or a different version of, for example, a GitHub version of the application. This way, you can have your stable system inside one container and another system running in a different container and using different libraries. So you are segregating, decoupling a different system, but you can still make them call together.
Excellent. So it's more secure than, for example, using a virtual environment.
Exactly.
Okay, I'm going to do our code word now. Some of you joined us late, so you didn't hear about the giveaway. I'll tell you about what we're giving away. It is an Arduino product. It's the Nano 33 BLE Sense Revision 2 with headers. And it's a versatile microcontroller. It's perfect for advanced IoT and edge applications. It's got Bluetooth low energy connectivity, multiple sensors for motion tracking, environmental monitoring, and sound detection. And the giveaway page is over here. Sorry if you didn't see that. That's the device. And there's the giveaway page. Let me put the URL on screen. And the code word, I think it's the shortest code word we've ever had. Nice and simple. X8. So just drop X8, doesn't matter the case, into the box there when you enter. And 5 lucky viewers will win one of those. Okay, let's get back to questions and comments. Jens asks, could you please show quickly again how you trained the model in Edge Impulse? It went quite fast, but probably interesting for the leaders.
Yeah. So just a moment. I will add to the Edge Impulse documentation.
While you're doing that, greetings to everyone. Selection from around the world. Patrick, Jeff from Scotland, Julian Rodriguez, Tunisia, Italy. Frank is with us again from Belgium. And we've got an intelligence sensor in the Netherlands that tells me by the name of Renee Bosch that it's raining in the Netherlands.
Okay, so the web page I started from, it's the end-to-end tutorial from the Edge Impulse documentation. Brian, if you can share my screen. Okay, so just head to Edge Impulse documentation and scroll to the end-to-end tutorials and choose sensor fusion. This is the tutorial I followed step by step. So it is actually pretty simple. You need to build your data set. There are multiple ways to do it. You can do, for example, in this case, using directly an Arduino board connected to a sensor. For example, in case of the Arduino 33 BLE Sense, you don't need to connect any sensor because it has a lot of sensors on board, as Brian was telling. So you can just write a sketch that captures the data and output it on the serial port. So I shared this a very simple sketch for doing it in the repository. So it's pretty simple. This is using an external sensor, but the overall idea is the same. So you read data and just create a line containing the values that you need to recognize or to use for your classification, separated by a comma. So a classical comma separated value line. And then you output it on the serial port. From there, you can use the Edge Impulse forwarder tool, which is something that you can install in your PC that connects to that serial port and bridge the data coming from the board or the sensor to your Edge Impulse project. Everything is documented on this tutorial and in other tutorial linked in the documentation. So you collect your data. Everything can be done automatically. Also, you can collect data offline, for example, using a different setup, collect it using a CSV file, and then upload that file on the Gimpulse project. It's the same. It depends on your preferences and on the tools that you have available. And I simply got through the tutorial. So I labeled my room A, room B, room C. You can label whatever you want. And then I designed the impulse using the instruction provided by Gimpulse. Selecting all the data I wanted to analyze. So in my case, I just analyzed the temperature, the humidity, the pressure, and the gas. Then I flattened the block, just leaving all the parameters as default, as suggested in the tutorial. Then I checked that there were enough separated features in order to recognize the different kind of board, and this means that my data collection was good enough, and that the model is able to select the different class, the different room that I want to recognize. So then I simply let run all the automatic, all the magic that Impulse does in order to generate the model. And as I was telling you before, the most important stuff is the deployment of the model. So in this tutorial, Gimpulse suggests to deploy the moment on a very hardware, so a Linux machine, an Arduino board, or whatever they support. In my case, I choose Docker. And then at the end, they just created for me the Docker image containing the model and told me the parameter that I need to run the container. So pretty simple.
Well, that was a very in-depth answer. I like the way you end off with pretty simple. But now I want to try it. And if anyone else is like me and wants to try this on the Nano BLE Sense, if you're lucky enough to win one, good luck. If not, I'm not eligible to enter the competition, so I can get one from the Elektor store. And yes, I would love to try that tutorial that you just showed. Alina has a question. Any challenges that the A53 cores address when running AI machine language models compared to traditional embedded systems? Seem to be losing you a bit.
Actually,
okay, you're back.
It's a generic. Yeah. Actually, the A53 class of ARM processor are generic application processor. There is nothing special in them to accelerate machine learning tasks. On the market now are available both microprocessors embedding NPUs, so units, hardware units capable to run specific tasks, specific loads for machine learning. Also, you can add external sensors using MPCI connectors or USB connectors, so for example, Coral or whatever, or any system like this that can be used to offload the machine learning loads to these specialized offload processors. So it's just a way. A53 has nothing special, but nonetheless, it is quite capable to run for running machine learning application. This kind of edge impulse edge AI machine learning application, because regarding, for example, sensor fusion, these models are pretty simple and doesn't require a lot of power. A different use case might be, for example, doing machine learning on photos or videos, and in this case, you will need a special microprocessor or an external unit to offload the machine learning tasks.
Okay, well, great. Thanks for that. McDonald wants to know, why can't someone rewind a few minutes? Well, this will even be online on YouTube, so if you want to rewind, you can rewatch the show. That's great. We've got about 8 minutes to go. Get to some more questions. I saw an interesting one here. Does Arduino provide guidance with regards to which Arduino devices we can use for common use cases? For example, what is the limit of use cases that can run on a BLE Sense without external hardware?
Actually, there are a few projects, for example, TensorFlow Lite or other library that are streamlined for running machine learning application inside microcontrollers, so not so powerful processor, which are amazing and they can do a lot of stuff pretty well. Of course, you cannot expect to run a people counting application at 60 frames per second on a microcontroller. But in other case, for example, recognizing noises, recognizing voices, doing sensor fusion, or this kind of application when you can get data from typical sensor that you can connect to Arduino devices. They are very, very capable. And platforms such as Giampaolo, Newton AI, or whatever that allows you to generate models optimized for microcontroller are pretty awesome. Of course, you can do it also entirely by yourself, creating your model, for example, using TensorFlow, and then optimizing them using TensorFlow Lite or whatever. There are a lot of open source resources available to deploy and to optimize your machine learning application on microcontrollers. And what I can tell is that every kind of microcontroller, starting from M4 class cores, moving to M7 or whatever, I think that they are enough capable of running very, very interesting machine learning application and doing edge AI tasks.
Another one from Chip Micro. So is it possible to run on X8 or on Windows without changing code? I suppose that relates to the containerized nature of it.
Yeah, exactly. It can be done, especially when you run Python application, because Python it's not compiled, so it just uses the interpreter available. And in case that you need to run application which needs to be compiled, you need a way to compile your application inside the container, starting from the target architecture. So typically you are running your Windows system on Intel x86 microprocessors, and this is different from the microprocessor architecture which runs on the X8, which is an ARM 64, And then if you, for example, write an application in C++ or in C, you need to follow the documentation in order to be able to compile your application for the target architecture. Okay, this can be done entirely in Docker using layered builds. In case you use scripting languages such as Python, you just need to use the proper image. And as of now, there are plenty of images supporting any kind of target architecture. So, for example, the basic Python images or the basic Go or Java or Node.js images are available both for ARM64, for x86, also for strange architecture like PPC or whatever. So as soon as you follow those guidance and you pay a little attention, it's totally possible to run the same container on two different architectures and machines.
Great. And then I second this from D. Conti. Interesting. Thanks.
Welcome.
We have 3 minutes to go, so we'll take one more question from Mark Gent. The project uses message pack as comms between the A53 and the peripheral processor of a shared RAM transport. Where can the details and libraries for that transport be found?
Let me show a slide. I was expecting this question, and I have a few slides for you. So the actual architecture is that one. We have the IMX8, which is the Linux microprocessor running on X8, and the STM32H7. There is something between them in order to make the RPC methods possible using a message packet RPC. And actually, there is an SPI bus which is connected between the IMX8 and the H7 itself. So it lands actually on the M7 core, which runs a specialized firmware that allows us to share a few specialized peripherals such as CAN, I2C SPI to the Linux microprocessor, and then those firmware relays the request from the RPC to the M4 core. From the M7 and the M4, we are using a shared memory technology based on OpenAMP. What actually happens is that a program talks, let's go forward, talks with an agent that is running on the Portenta X8, which is called M4 proxy, which is connected to the special device, which is connected in turn to SPI, which in turn is connected to M7, and then the M7 is connected to M4 using OpenAMP. So it is pretty complicated architecture that allows you to implement this kind of RPC. The overview of this architecture is that you have a program which is talking to the M4 proxy, which is talking to the device, which is talking to the H7 and then to the M4. You can launch calls to the M4 proxy, and they will rely to the M4. And also you can offer as an endpoint for calls to be called from the M4. Those are two different mechanisms, and there are plenty of examples on the repository for Portenta containers that show how to implement the different kind of channels. So sending requests from the Linux application to the M4 and getting and sending requests from M4 to the Linux application. A message pack RPC runs on top of this channel.
Great. And I agree once again with Ben Martins. Perfect explanation there. This is complex material, so I would recommend taking another look at it, and it will be available on our YouTube channel. So I will check it out again, and I'm glad that I started with Docker, but you've encouraged me to keep learning more about Docker because it seems quite it's able to make your app compatible across many platforms and secure and blocked off, kind of like a sandbox. So yes, I will learn more about Docker. And thanks to Alessandro for saying excellent webinar, clear and effective explanation. And Peter Gilbert, thank you both. It was more Giampaolo than me. And thanks to Pussy for your thanks over there. We have now reached the top of the hour. We're out of time. Thank you very much to everyone joining us from all around the world. I see more than 200 of you are still with us, so that's great. We'll let you enjoy the rest of your day, evening, morning. And Giampaolo, thank you very much. Very good explanations.
Thank you too, Brian.
Very packed with information, so definitely worth another watch. Giampaolo is Senior Customer Success Engineer at Arduino Pro. It's the pro end of Arduino. Thank you very much for joining us, and thanks to everyone. Goodbye.
Bye.